And in light of the fact the other two guys aren't here yet, I guess we'll go on and get started. You said there were no questions on what we've done so far. We're in Chapter 2, Matrices, Section 2.2, Properties of Matrix Operations. We're on page 53, beginning with Theorem 2.2, Properties of the Zero Matrix. We just had introduced the zero matrix earlier, and there is a little remark here that we'll get to that in a minute. I'll introduce that where it is. Now, the question is this better typed or written? I'm going to type it, I think. I know my typing's terrible, but probably it'll be easier to read in the long run. Okay. Make sure nobody else is here. This is a little late for some of them to be coming in, but yep, just the two of us. Okay. So these are properties of the zero matrix. So here's a given. If, well, my thing isn't typing. Okay, let's try it again. There we go. If A is an m by n matrix and C is a scalar, then the properties or the following properties are true. Okay. Okay, here's the first one. Okay. A plus the zero matrix. Now I'm going to just make it, I can't designate that a matrix. You just have to understand, but this matrix has to be an m by n matrix. So those are supposed to be subscripted m and n. So that's a capital 0 would have been a bold 0 if I could do a bold. But anyway, that any matrix A, m by n matrix A by an m by n zero matrix is always going to be the original matrix A. Number 2, matrix A plus the opposite of matrix A is always going to produce the zero matrix. Okay, and that again, whoops, zero matrix, and that will be an m matrix as well. Those should be subscripted. I can't subscript in this module. Okay. 3, if C, if that scalar C multiplied by our matrix A, m by n matrix A, if that happens to equal to the zero matrix, okay, and again I can't bold it or anything, but that would be the m by n matrix. If that's true, and m and n should be subscripted there, if that's true, then one of these two things has to be true. Then either C has to be identically equal to 0, that's the number 0, or A itself has to be the 0 m by n matrix. Okay? One of those has to be true. Now for some reason it jumped up in size, and let me see, I might have to, no, I think this is going to work pretty well. Okay. That's Theorem 2.2. Now, just to tie in a little bit of nomenclature here, this first one is basically saying the proper size zero matrix, same size as your A matrix, the MN0 matrix, M by N0 matrix, is the additive identity element for an M by N matrix, any M by N matrix. You add to any M by N matrix a 0 M by N matrix, you're going to wind up with the matrix you started with, the additive identity element. The second one here is saying that negative A is the additive inverse of A, which makes sense. It's the opposite of A, because the two of them add to be the 0 M by N matrix. The 0 matrix is M by M size. Just like 17 plus a negative 17 equals 0, 17 and negative 17 are additive inverses of each other. Now this is the one that would be closest to what we call the zero product principle. If some scalar C is multiplied by some matrix A and you wind up getting the M by N 0 matrix, then guess what, folks? Either that C was 0 or that A was a 0 M by N matrix to begin with. No choice about it. One of those has to be true. Okay? Kind of our zero product principle for matrices. Okay. And then they have a little blurb before they get to example 2, which is making a correlation between real numbers and matrix and some of the properties of those. So I think I'm going to go to my pen here and do these. What if you had, guess what, this is linear algebra, so what if we had a linear equation x, well, I'm in lavender, let me go back to black. My last class we were doing multiple things. X plus, say, some number A, and you knew that was equal to B. How could you solve this for X? We would subtract A from both sides, and you would get X is equal to B minus A. Okay? Now, the reason that's true is plus A, come on pen, come on, okay, there you go. Plus A minus A adds to 0. Okay? Well, in matrix speak, if you had some unknown matrix X that we're looking for, these are capital now, plus some known matrix A, now of course they have to be the same size, okay? Otherwise you can't add them. So if X is N by M, M by N, A has to be M by N. And they add to be some matrix B, which of course would also have to be M by N, the proper size. What you can do is subtract matrix A from both sides, and that would then give you, because of this property right here, that would give you the 0 matrix. Then you can say X, the new matrix X that you're looking for, is matrix B minus matrix A. Of course, they all have to be the same size. Now, that gives us the tools we need to do example 2. And I think we'll need more space than what we have, so let me clear these. Any questions on this before I clear? All right. Still just the two of us. I don't know. What's happening today? Okay. My first class was well, it turned out being a good sized class, but it sure started a bit small. So here's example 2. What we're trying to do is solve for matrix X in this equation. 3x matrix X, capital X, plus matrix A is equal to matrix B. Now, of course, all of these matrices have to be the same size. Well, they give us two of them. They give us that A is equal to 1, negative 2, 0, 3. and that matrix B is equal to -3, 4, 2, 1. Okay. Now, if you're looking for X, that's what we're trying to find. This is what you're trying to find. What we're going to do is subtract matrix A from both sides because they are the same size. You can subtract them. Okay. This adds to the 0 matrix here by the second principle we did before. And then what we got is 3 times matrix X is equal to B minus A. Now you could plug and chug. I'm chugging and plugging because I'll just do everything. And then I'm going to divide both sides by 3, which is the same as multiplying by 1/3. Okay, so that's going to give us the answer we need. So that's going to be 1/3 of B minus A. So let's see if we can do that up here. Entry by entry. -3 minus 1 would be a -4. 4 minus a -2, that would be 4 plus 2, would be 6. 2 minus a 0 would be 2. And 1 minus a 3 would be a -2. Okay? Now I'm almost perfectly happy to see you leave the answer in that form, but I'm almost certain the book is going to multiply that 1/3 through and make this -4/3 to 2/3 -2/3. And let's see if that's what they got. -4/3 to 2/3 -2/3. Good for them. Does that make sense? Any questions? Okay. Make sure I'm recording so the other guys can... Oh, here comes James. Good deal. Doubled the class size. Okay. You hold on just a moment until I can get James marked present. Okay. Top 2 are here. We're missing the 3rd. All right. Now, putting a little extra pressure on Jesus here. I've got all my Monday, Wednesday classes on the same page as this one Tuesday, Thursday class because they're all fairly small classes in my grade book. And yesterday, if you recall, and I think you weren't here for the first one, but I think I told you, we had perfect attendance all day long. And right now, we're one short of perfect attendance today. That would make the second half of the week perfect attendance, second half of week. So I hope Jesus gets here. So much easier putting attendance in when they're all present. It's just so much easier. All right. Now, what we dealt with so far: addition of matrices, subtraction of matrices, multiplying a matrix by a scalar constant, so matrix multiplication. Now we're ready to start matrix multiplication. What did I say? Scalar multiplication. Now we're ready to start matrix multiplication. Okay? Now, remember, it's a different animal from adding and subtracting matrices. So here's the theorems we're going to use here. I'm going to clear the screen. And I don't know. I guess I'll go on and type these into... My writing is pretty bad. My typing's bad, but the typing, at least when I make all the corrections, gets a lot more readable. So here is theorem 2.3, properties of matrix multiplication. Okay? So here's the given here. If A, B, and C are matrices, good deal. Now, here's the catch. With sizes such that the matrix products are defined. We'll go back over what that means in a bit. Okay. And C is that good old scalar. Then these properties are true. Okay. I'm just going to leave that. Okay. These properties are true. First, if you had matrix A multiplied by the product of B times C, that's got to be equal to the product of AB times C. Okay, that's the first one. The second one, what if you had matrix A, second one, matrix A multiplied by the sum of B plus C. That's going to be equal to AB plus AC. Third one. Drives me nuts. This is such an inconvenient keyboard. Looking gift horses in the mouth, but okay, this one starts off parentheses A plus B, close parentheses, times C would then be equal to AC plus BC. Okay. And the fourth one. Yuck, off again. Okay. The scalar C, and you had to use it somewhere here, times the product of AB is the same as, equal to, the product of CA times B, which is also equal to the product of A times CB. Okay. This will only straighten up. All right, got it all in one line. There are the four properties. Now, I'm going to fiddle with those a little bit. Okay? I'm going to see if it'll let me do this. Now, remember it says sizes such that the matrix products are defined. Okay? For that first one here, this one here, let's just say that A, oh, it's not going to let me write there. Okay, I'm going to come down here. Oh, wait, no wonder it won't let me. I'm in the wrong mode. Well, what happens if I'm trying to move something, if I've got two pads. If I have this pen too close to the other pad, my finger won't work on the first pad. Okay, so anyway. Now, all right. Oh, yeah. For this number 1 up here, let's see if I can write here now. Let's just say that A, favorite size, M by N. Okay? Now, I really shouldn't have started there. I should have started with, in fact, I think I'll erase this. Oh my goodness gracious. It erased my whole thing. I didn't know it was going to do that. Okay. so much for my clever idea. So let's just write that first one again, that A times BC is equal to AB times C. Oh, and I forgot to write on the side what those were. This one is the associative property of, I would say, matrix multiplication. Okay. I don't like just calling it multiplication because matrix multiplication is not quite the same. I'm going to start with matrix B here. And let's say B is an M by N matrix. Now you tell me what C has to be. Maybe not everything C has to be, but at least something C has to be. The number of rows of C has to equal the number of columns of B. So that means it has to be an N by something. So let's just call it an NP matrix. Okay? So if you multiply these together, that's going to give you a matrix which is an MP matrix. Now, what does that tell you about A? A has to be something, and let's just call it Q by M. Otherwise, you can't multiply those together. So this product is an MP, that's a Q. So this product over here has to be a QP product. Q rows, P columns. Now, let's do the same thing we did there. We said A here was QM, same A, so it has to be the same, times B, which we said was an MN from the get-go, and multiply that by C, which we just arbitrarily, not totally arbitrarily, named it NP. Okay? Well, these two multiplied together, since these two are the same there, you can multiply them, so that product is going to be a Q by N, and you can certainly multiply Q by N by an N by P, because the N's are the same, and your result is a Q by P. And that's what we had here too. I put the time sign in one of them, but not the other. Okay, so at least size-wise, we know this makes sense. Size-wise. You have to verify the numerical part later, but the sizes make sense. Okay? Now, let's see if I can get this to do, and we'll do the second one. All right to erase? Because the second one, everything changes on the sizes. Or the overall changes happens. Okay? Now the second one of these is A times B plus C is equal to AB plus AC. Now, let's see what we know have to be true about the, oh, here comes Jesus, otherwise known as Miguel. Perfect attendance, ding, ding, ding. Way to go, folks. Yuck, I just dropped my pad on the floor. This is a pain in the neck, having to have things scattered from dresser to desk to bed. I just don't have enough room for anything here. I hope my pad still works. Okay, so let's see the sizes again. We're going to start just like we did before and call B and M by N. Okay, and we're going to add that to C. What does that mean? C has to be. No doubt about it here. What size does it have to be? M by N. Now, by the way, Jesus, you just got here, and I think I forgot to say this when James came in too. We're in Chapter 2, Matrices, Section 2.2, Properties of Matrix Operations, and we're doing the properties of matrix multiplication. Did we already do these last time? I just noticed my mark. No. Okay, that was a mark from last term. Okay, never mind. And we're on page 54 doing the theorem 2.3, or at least outlining it. To add two matrices together, they've got to be the same size. So therefore, the sizes we had before don't work anymore, but they're whatever appropriate size. Now what does that make A having to be? Because the sum of these is going to be an m by n matrix, right? Because both of them are m by n. You add m by n. The product has to be m by n. That means A can be anything for a initial. Let's call it P by m. And that way you can multiply those together, and your answer here will be a P by n. Okay, let's do the right hand side. Using the same things we had before, we said A was a PM, that means evening, no, P by m matrix, multiplied by B, which was an m by n. I can't get that n to right. Okay, there it goes. And add to that A, which was a PM, by C, which also was an m by n. In this case, it wasn't in the last one. These two are the same, so we can multiply them. These two are the same, we can multiply them. This product will be a P by n, plus this product is going to be a P by n, and the sum of two P by n's is going to be a P by n, and sure enough, those two are the same. Now, at least size-wise, this makes sense. Okay? Now, and by the way, that was a distributive property. Okay? It's the distributive property. And they just leave it like that. Distributive property. I like to go on and put of matrix multiplication over matrix addition, because later we'll introduce some other things that aren't matrices. So that's that one. So all right for me to erase the rationale at the bottom. Okay, let me see if I can do it here. This may be easier. Yeah, this may be a little easier, though I tend to fly off the handle sometime. See, I have two pads. One's a finger pad and one's a stylus pad. And most of the time, the stylus pad's easier to operate, but I think with erasing, it's perfectly okay to use the finger pad. All right, the third one here was A times another distributive property. This one was A plus B times C was equal to AC plus BC. Now, one thing to mention here, notice sometimes they put something in front, sometimes at the end. In matrix multiplication, the order matters. Notice there is no commutative property here. There's only associative and distributive. You cannot commute the matrices. So therefore, if you put them this way, you have to keep them that way. Okay? And this is another distributive property. Everything here is the same. Matrix multiplication over matrix addition. I'm not going to write all that out again. Okay? In this case, A can be, let's just start with an m by n. And if A is an m by n and you're adding it to B, B has to be an m by n. No choice about it. C, though, has a little bit of choice, not much. The number of rows has to be n, but the number of columns could be anything. We'll call it P. So this is going to add to B an M by N, multiply by an N by P, and you can sure do that multiplication because I chose well, and that gives you an M by P answer. Well, let's see what we get on this side. The A was an M by N. That is a really ugly M, okay? And the C we said was an NP, and you're adding to that a B, which also was an MN in this problem, times the C, which was an NP still. These certainly can multiply because those two are the same, giving you an M by P matrix, and you can add to that. These two can multiply because they're the same, an M by P matrix, and certainly that will give you an M by P matrix, and that's exactly what you got over here. So at least by sizes, these things have to be true. Okay, now let me see if I can go up and do the erasing easily again. I don't know if it's any easier, it just feels easier than rubbing the stylus on the pad. Okay, because I just worry about that. Those things are really expensive. My finger isn't, so I can do this till the cows come home and it won't really hurt anything. Okay. Excuse me just a minute. It's past my lunch time and I'm starving. My stomach was growling in the last class. Okay, the fourth one here, sorry, is, where in the world is my pen? There it is. C times AB is equal to CA times B, and it's also equal to A times CB. Let's just check, and this is they don't write it down. It's kind of an associative property of two matrices and one scalar. So it's a bit bizarre. You can move the C around because it's a scalar. You can't move around matrices like that. So this is a lowercase c, capital A and B. All right. Well, of course, if A was an M by N, then B would have to be an N by something. So let's just call it P. And C, of course, is just a scalar. Well, this product is going to be, because these two are the same, an M by P, and you multiply that by a constant C, you still get an M by P, okay? It's just you multiply every element by that. Well, this is going to be the same thing too. This will produce an M by P, M by N, and this will produce an N, this is an N by P, and you can certainly multiply those together and get an M by P, and the C will be still multiplied. This was an M by N, and this turns out being an N by P, and you can multiply those together and give you an M by P. Okay, so at least by size they work. They don't list a title for it because it's a little convoluted. Okay. Any questions on that theory? Probably spent way too much time on it, but just so you get the concept. Okay, let's clear those drawings and do example 3. It says find the matrix product, if I can find my pen, ABC by grouping the first factors as AB and then multiplying by C and showing that's also equal to A times BC, where A is the matrix, (1, -2, 2, -1), B is the matrix, excuse me, I shouldn't have eaten that. Now I'm thirsty. Okay. B is this matrix, 1, 0, 2, 3, -2, 1. And now am I going to have room to fit C in here? Let's see if we can. That's a capital C. It doesn't look like it. And that's -1, 0. Yuck! I don't know what that means. I don't know if you can see it or not. A -1, 0. Three, 1, 2, 4. All right. Now, first thing you have to ask yourself, can you multiply these two together? Can you multiply AB? A is a 2 by 2. B is a 2 by 3. Yes, you can. That will give you a 2 by 3 matrix. So when you multiply those two together, you'll get a matrix that's 2 rows, 3 columns. 1, 2, 3, 1, 2, 3. So this first entry here is the 1, 1 entry. So we multiply the first row of A by the first column of B. It'll be 1 times 1 is 1, plus a -2 times 3 is -6. 1 minus 6 is -5. The next entry here is the 1, 2 entry. So we do the first row again of A by the second column of B. 1 times 0 is 0. -2 times -2 is +4. The 1, 3 entry here will be first row here, third column there. That would be a 2 minus 2 is 0. All right. I should never have eaten anything. Now my stomach is even hungrier. Let me see if that will sate it a little bit. All right. Now, this entry here is the 2, 1 entry, so we'll do second row of A by the first column of B. That would be 2 minus 3 is -1. 2, 2 entry, second row by second column, will be 0, 2 plus 2. So that's going to be a 2. And then the 2, 3 entry here is second column here, second row here, third column here. That would be 4 minus 1 is 3. So there's the AB. And last, while we got it here, multiply that and do AB, which we have here, times C. Well, AB we know to be a 2 by 3. We just determined that. C's a 3 by 2. So sure enough, we can multiply them together. Our result is going to be a 2 by 2. So that means it's going to be blank, 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 blank. So how do we get that? This is the 1, 1 entry here. First row, first column. So it will be the first row of AB times the first column of C. So it will be -5 times -1 is 5. Plus 12 will be 17 plus 0. So that's going to be a 17. The 1, 2 entry here will be first row here by second column here. That would be a -5 times 0 is 0, 4, and then another 0. So that's just going to be a 4. Okay. The 2, 1 entry is second row here. First column there, that's going to be a 1, plus 6 is 7, plus another 6 is 13. Lucky 13. The 2, 2 entry here is going to be second row by second column, and that's going to be a 0, 2, plus 12 is 14. Alright, so that's the A, B times C. Now what we need to do is A times BC. Okay? Okay, well what is B? B is a 2 by 3. Multiply that by 3 by 2. And sure enough, the 3's are the same. So you can cancel those out, and you're going to get A times a 2 by 2. That should be a square bracket, not a parentheses. Oh my goodness. Alright, I'm trying not to eat anything else. That was a dead end. So let's see if we can multiply B by C. That's what we're doing, BC. So this is the 1, 1 entry, so it'll be the first row of B by the first column of C. That's be a -1 plus 0 plus 4, so that's going to be a 3. The 1, 2 entry, first row here, get out of there, first row here, second column of B, that would be a 0 plus a 0, 8. Are y'all doing this too? I hope you are. I just usually wait for you to answer. I never hear anything, so I've just started just talking myself. So the 2, yeah, this is the 2, 1 entry here, second row of B times the first column of C. That would be a -3 minus 6, that would be -9 plus 2 is a -7. And the 2, 2 entry here would be second row of B, second column of of C, and that would be a 0 minus 2 plus 4, that would be a 2. Alright, now we've got to multiply that by this one. I'm going to write them next to each other. That would be a 1, -2, 2, -1 times a 3, 8 and a -7, 2. Alright, this is a 2 by 2 times a 2 by 2. These inner 2's are the same. Your result is a 2 by 2. The first one's a 1, 1 entry, so it'll be the first row of A by the first column of BC. So that'd be 3 plus 14 is 17. Looking good so far. Okay. Second entry is the 1, 2 entry, first row of A times the second column of BC, and if I can read my writing there, that's a 8 minus 4 is 4. Whew. So far so good. This entry down here is these 2, 1 entries, so it'd be second row here, first column here, that would be 6 minus 7 is a minus, whoa, yuck, 6 plus 7, because that's the second row, first column, 3 times 2 is 6, -1 times -7 is a +7, 6 plus 7 is 13. Wow, almost messed that up. Okay, and then the 2 entry here would be second row here by second column here. That would be a 16 minus 2 is 14, and I believe that's exactly the same as what we got there. Now, this doesn't prove the theorem, but it sure seems like it's a good indicator it's probably true. 17, 4, 13, 14. Got it. All right. Now, let me get some more water. I've been talking almost nonstop since 8:30 this morning. The throat, and all week long too, so the throat is getting ready to give it up on me, it feels like. Now, here is one of the things I stated before. You have to remember it's not true. Many of these things look reminiscent of whole numbers, like associative property of multiplication, distributive properties, those kind of things. But remember I said commutative property does not work with matrix multiplication. And this example is indicating this. It seems like we've had this before, but maybe not. Let's do it now. What we want to do is look at matrix A here, which is fortunately a simple little 2 by 2, 1, 3, 2, negative 1. And a matrix B is 2, negative 1, 0, 2. Okay? Now, what we're considering here is what's the product AB. So that's not too bad to do. AB, A is a 2 by 2. B is a 2 by 2. The product will be, guess what? A 2 by 2. Okay? So let's write it down. Blank, 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 blank. All right? First entry here is the 1 entry here. So we'll do first column of A, first row of A by first column of B. 2 plus 0 is 2. Second position here is the 1, 2 position. First row, second column. So we'll do first row again here by second column here in B. That gives you a minus 1 plus 6 would be a 5. Okay? This entry here is the 2, 1 entry here. So we use second row of A by the first column of B, and that would be 4 plus 0 is 4. And then the 2, 2 entry here, second row, second column, we'll do second row of A, second column of B, and that gives you a minus 2 would be a minus 4. Alright, so there's the product AB. Now we want to compare that with the product BA. So I'm going to repeat A so it'll be over here on the correct side now, which is the right side as well. That was a 1, 3, 2, negative 1, same A, but now we're going to look at the product BA. Well, let's make sure we can even do that. B is a 2 by 2, A is a 2 by 2, and sure enough the inners are 2's and your result is going to be a 2 by 2. So this is also going to be a 2 by 2. So the sizes are the same. In this case, I say that emphatically for a reason. We'll come back to that in a minute. First entry here is first row, first column, so we'll do the first row of B this time, first column of A. That would be a 2 minus 2 is 0. Give it up, folks, it's already different. The 1, 2 entry here is be first row, second column, 6 plus 1 is 7. Nowhere close. 2, 1 entry down here will be second row here. First column there, that's 0, 4. Hey, one number came out the same. That's just happenstance. And the 2, 2 entry here would be second row, second column, which is the 0, minus 2. Let's make sure we did it right. 2, 5, 4, negative 4, and 0, 7, 4, negative 2. And obviously, AB is not equal to BA. Nowhere close. Now, they say that, and then they say this: do not conclude from this example that it's never equal. It's in general not equal. There are circumstances for which AB and BA will have the same result. Rare, but it does happen. Okay, so usually we say they're usually not equal. They do give us this example. Let me see if I can do it down here. Just like before, A in this case, different A, 1, 2, 1, 1. And B is 2, 4, 2, 3. So let's see what AB is. I'm not going to go through all the sizing. We already know it's going to be a 2 by 2. Okay, first row, first column. 2 plus 4 is 6. First row, second column. 4 plus 6 is 10. That's a 10. It's an ugly 10. Second row, first column. 2 plus 2 is 4. I really high level math today. And second row, second column. 4 plus 3 is 7. Now we're going to do the same thing we did before. I'm sorry, I'm losing the voice completely here. Well, the good news, I only have 4.5 hours this afternoon after this class. That's funny. 1, 2, 1, 1. And now let's do BA. And we know already that's going to be a 2 by 2. So we won't go into that gory detail. And let's do the entry. First row, first column. 2 plus 4 is 6. That's the same. 4 plus 4 is... Ooh! How did I miss that? Let's go back and redo this one. Y'all should be doing it with me. 4 plus 6, sure enough, is 10. And here we have 4 plus 4 is 8. Did I copy the problem down wrong? Yes, I did. And you let me get away with it. That was a minus 2, 4. Where my brain was, I was looking at the wrong B. I don't know where I got that B from. Oh, we got to go back and redo all this. Or a lot of it. I'm surprised anything came out right. Okay. Minus 2, 4, 2, minus 2. I just copied the wrong problem. This is a minus 2 down here. Okay. Let's redo that. First row, first column. Minus 2 plus 4 is a 2. Yuck! Now it starts doing this mess. 2. First row, second column, 4 minus 4 is a 0. Second row, first column is a minus 2 plus 2, that's a 0. And this one is a 4 minus 2 is a 2. Okay, I'm guessing this one's wrong too. Okay. Excuse me a minute. Throat is going bye-bye. Voice is going bye-bye. Okay, 2, 4. First row, first column, negative 2 plus 2 is 2, check. First row, second column, minus 4 plus 4, 0, check. Second row, first column, minus 2 plus 2 minus 2, 0, check, check, check. And second row, second column, 4 minus 2, 2. Yes, yes, yes. Now, if you think that's a little suspicious, I'm not sure you think this way, but in case you are thinking, isn't that a multiple of our identity matrix, which would have been 1, 0, 0, 1? You're absolutely right, and I won't want to say every time, but I'll say in the vast majority of times that AB is going to be equal to BA, which is very rare, but in the vast majority of those times, you're going to have a multiple of the identity matrix. Almost guaranteed, okay? But anyway, we've done that. Let's move on to example 5. Any questions on that before I leave it? Are y'all still with us? Okay. I'll go clear the drawings here. Now, here we have 3 matrices. The first we're going to name, guess what? A. That's going to be a 1, 3, 0, 1. The second of these, I'm guessing, is going to be that one I copied wrong before. And that's a 2, 4, 2, 3. And the third one, C, is going to be 1, negative 2, negative 1, 2. Okay. Now, what they're asking us to do is to show that AC is also equal to BC. Okay. So AC, I'm going to write down C again here so we can do it a little easier. 1, negative 2, negative 1, 2. Now, AC, now that I've written them closer together, it makes it a little easier to do. And again, this is a 2 by 2, that's a 2 by 2. The answer is going to be a 2 by 2. Not because they're the same, but because the inner and the outers, the two outer things are 2 and 2. Okay, so let's do first row times first column. That's 1 minus 3 is a negative 2. First row, second column, negative 2 plus 6 is a 4. 2, 1 is going to be 0 minus 1. And 2, 2 will be 0, 2. Okay. Now, let's do BC. Those are already close together. So I think it's going to be fairly easy to do. 2 by 2 by 2 by 2 is going to be a 2 by 2. Okay. First row, first column is going to be 2 minus 4 is a minus 2. Oh, so far that's correct. First row, second column, minus 4 plus 8 is plus 4. Next one, 2, 1 is going to be a 2 minus 3 is a minus 1. Yep. And then 2, 2 is going to be minus 4 plus 6 is a 2. Sure enough, these two are equal to each other. Okay? Now, let's think for a minute. If this were numbers, and we had little a times little c is equal to little a times little b, we would divide out the a's, and you would conclude that little c is equal to little b. And that would be absolutely true with numbers. But we can see right now b and c are anything but equal to each other, so that principle doesn't hold for matrices. Guess what? We haven't defined division of matrices. We're not going to define the division of matrices. Adding and subtracting were fairly similar to each other. They made sense. Multiplication was very different from adding and subtraction, so it didn't make the same sense. And division isn't even defined. So you cannot go around saying, oh, if matrix AC is equal to matrix BC, then divide out the C's and you get A equal B. No, it wasn't. It was nowhere close. A and B are nowhere close to equal to each other. Okay. Now, oh my, maybe I jumped the gun on you. I thought we had already had this, but I guess we haven't. Have we not introduced the identity matrix before, or have we? I just mentioned it earlier, and then I realized maybe we haven't even covered it yet, but I thought we had. I've taught this course so many times I can't remember where we've had it. Okay? Let's start with a clean, clear slide. All right. We're going to look at a special kind of square matrix. Note that this matrix we're talking about now, absolutely without a doubt, has to be square. Okay? Now, this square matrix is going to look like this. Down the main diagonal are all going to be ones. Everywhere else is going to be a 0. Front, back, everywhere. Okay, that is the matrix we're dealing with. Special type of square matrix, same number of rows and columns. Okay, and I should have dots here, 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 and here as well. Okay, square matrix, ones on the main diagonal, zeros everywhere else. We give it the name I, the identity matrix. Since it's square, we only put one subscript because the number of rows and number of columns are the same. It's square. So this is a n by n, or just a IN, and that would be just like I described. I see no reason I need to get down again. That's if you had n rows and n columns. Okay, that would be your I sub n. So the very simplest of these, which we usually don't do, would be I sub 1. Okay, well, guess what? only one entry in it, and it has to be a 1 because the leading value always is a 1. Now, I2, anyone want to tell me what it would be? One zero zero one. I3, one zero zero 0 1 0 and 0 0 1. Okay. So I sub n means identity, and they call it I for the term identity. Now you might say, why? Well, a little bit of the reason. What is the multiplicative identity element in numbers? It's the number 1. Okay? And what we'll find out, and notice the main diagonal are 1s, everything else is 0, we'll find out the identity matrix acts a lot like your multiplicative identity, the number 1 in real numbers. Okay? So that leads to the properties of the identity matrix. And let me go to a clear screen, and I think since I've been typing them in, I'll type this one in as well. Okay, so let me get to the text, and let me get it here. If A, I can't type this, I must really be hungry. A is a matrix of size M by N, then the following are true. I'll just leave that blank. 1. That A, M by N matrix, times I, but this I has to be, because I is square, meaning same number of rows of columns, and since you multiply it by A is M rows by N columns, this I has to be subscript N. I can't do a subscript here. That is what you can multiply with, and if you do, you get the matrix A again. Just like multiplying number A by multiplicative identity element 1 gives you number A, multiplying matrix A by the properly sized identity matrix, that's the one with the same number of rows as A has columns, and of course I has to be square, so that would be an N matrix, then that's always going to be true. Number 2, it looks a lot like it, but slightly different now. I, but this time it has to be size M. That should be a subscript times A. Why is that? Because now the number of columns of I has to equal number of rows of A, which is M. So this is a different I from this one. All main diagonal 1s, all zeros elsewhere, but it's a different size. Okay, that will also equal A. Oops, left off the equal sign. I thought I had typed it in. A. Okay, so both of those are true. Now, I think we can at least get started on, and let me stretch this out a little bit. Okay. And I think we can get started on example 6. We may not be able to finish it, but let's get started. Let me get my draw thing in place. And let's see if we can put it here. Come on, pen, show up. There we go. Here's the A part. 3 negative 2 by 4 0 negative 1 1. Now if you're going to multiply that by an identity matrix, what size would it have to be? This is a 3 by 2, so this has to be a 2 by 2. No option there, it has to be a 2 by 2. 3 by 2 by 2 by 2, that certainly is going to give us a 3 by 2. Okay, because 3 by 2 by, and that's why it has to be a 2 by 2, because these two numbers have to be the same, and so this is square, that has to be 2 by 2, and that gives us a 3 by 2 here, and that's what we've drawn. So let's do it. First entry here, first row, first column, first row, first column. 3 plus 0 is 3. First row, second column, first row, second column. 0 minus 2 is minus 2. Second row, first column, second row, first column. 4 plus 0 is 4. Second row, second column, second row, second column. 0 plus 0 is 0. Third row, first column, third row, first column. Minus 1 plus 0 is minus 1. And third row, second column, third row, second column here is 0 plus 1 is 1. Yep, these two are exactly the same because we multiplied by the identity matrix, which gave us exactly the same result. So just like I thought, we weren't able to finish the whole example, but at least we got started. We did the A part. We will start with the B part next time. And I can't believe I don't have another error anywhere on this page. It means we got that whole, both pages done the last time I taught it, but not this time. Well, every time I've taught it, basically. So, homework exercises here, and we almost finished 2-2, would be any of the odds 1 through 5. They should all be at Calc Chat. They're also in the back of your book. Any of the odds 7 through 11, they should be at Calc Chat. 13 should be at Calc Chat. Any of the odds 15 to 21 should be at Calc Chat. 23 should be at Calc Chat. 25 should be at Calc Chat. 27 should be at Calc Chat. 29 should be at Calc Chat. And then you can start, now let's see, yeah, start working on 31 and we'll do 31. We'll just end there, pick up the rest of those later. Okay? Any questions? All right. Now, remind me, did I get your test out there for you? Chapter 1 test. I want to make sure I had, and I believe I did, but y'all tell me. I've had so many tests starting at the same time, I'm getting them crossed up, which ones I've posted. Did I post yours? Help me, somebody. Well, I'm not hearing an answer, so I'm going to assume it was posted properly. Okay?
I haven't turned mine in yet.
Yeah, but you've got it, right?
Yes.
Okay, good. That's what I'm asking. I did get it out there. Yeah, it's not due yet. You can work on it up until we're through with test, ready for test 2, which is going to be several sections down the road here. Chapter 2 has, goodness gracious, well, we're not going to do 2.5, so it has 4 sections. We're in 2.2, so we're not halfway through chapter 2 yet. So you got plenty of time. I just want to make sure I did get it posted. In one of my classes yesterday, I realized I had forgotten to post the test. So I got it done. All right. Any other issues, concerns, problems? I just stopped sharing. I was sick and tired of sharing. So unless there's some other questions, I'm going to end the meeting for all of us, reminding you, be safe, be careful. The virus is still out there, kicking. I want to say alive and well. Is sick. It's a sick virus, and it's going to move around. So please be careful. All right. If there's nothing else, I'll go on and end it. Take care. We'll see you next week. Okay? Bye-bye.